Integrated Science. This is Mr. B, and we're going to wrap up our section of the solar system, kind of almost in a backwards way. But this section talks about how the solar system actually originated. And I will admit that this can get a little bit complex with some of the terms here, so we're just going to do our best and we'll make sure we break it down more in class. But this section will talk about how the solar system originated. So any theory about the origin of the solar system must explain why all of the planets' orbits lie more or less in a plane and all of the planets orbit the sun in the same direction. It must also explain differences in size and composition between the terrestrial planets and the gas giants. So a lot must encompass any theory about where our solar system came from. And the one theory that we have that supports all those is what is called the nebular theory. So the nebular theory states that the solar system formed from a rotating cloud of dust and gas. So that's kind of just a general overview. Again, there's much more specifics in it, but we'll get into that now. So again, the generally accepted explanation for the formation of the solar system is the nebular theory, and it started to kind of give you some background. It's as a large thin cloud of dust and gas, like the one that eventually formed our solar system, is called a solar nebula. So according to the nebular theory, there was a solar nebula formed from material expelled by previous stars. So again, a solar nebula, what it is, it's a large thin cloud of dust and gas, like the one, so just a large thin cloud of dust and gas. Then according to the nebular theory, there were previous stars that expelled a bunch of that, and that formed a solar nebula, which gave rise to our solar system. So here is kind of, again, a little bit of a picture here. It says the contraction of the solar nebula, which is a large cloud of dust and gas, led to a disk-shaped protoplanetary disk from which the sun and planets formed. So they're going to talk about that more here. So again, here's the solar nebula, again, cloud of dust here. Again, they're going to talk about how the sun can form at the center. Then there's going to be things that are called planetesimals and things that are called protoplanets. So these are all, this is almost like kind of looking ahead of kind of what we're going to see here in a moment. But these are just kind of some of more of the vocabulary terms we're going to need to know. So it says that it's likely that a shock wave from an explosion of a nearby star caused a solar nebula to collapse. So there was a bunch of, again, a big cloud of dust. Again, a star exploded, caused a shock wave, the solar nebula collapsed. So as that cloud contracted, so as it kind of became smaller, it began to spin faster. As it spun, gravity increased and it became stronger as the solar nebula shrank. So this large cloud of dust and particles started spinning. As it spun, gravity started pulling things together, and then it kind of started shrinking down and becoming more dense. As the solar nebula rotated faster, it began to flatten out, and then over about 100,000 years, a large disk-shaped cloud of dust and gas called a protoplanetary disk formed. So I think that picture, again, protoplanetary disk right here. Again, the sun's going to form at the center. We'll talk about that again. So as the solar nebula collapsed, it spun, it formed that protoplanetary disk. The disk was densest in the center and thinner toward the edges. So again, nearly all of the mass of the solar nebula became concentrated near the center. This density increased until the temperature reached a few million degrees, and after about 10 million years after the formation of the solar nebula, nuclear reactions began and the sun was born. Again, this kind of makes sense. Again, if you think about some of the other things you learned, we learned earlier on that the sun had 750 times more mass than everything else in the solar system combined. So the nebular theory accounts for that. When it spun, most of the mass went to the center. Again, more mass. Again, the temperature rose as the spinning went on, and again, the formation of the sun began when the nuclear reactions were there. So that's kind of how the planet came to be there again, or the sun came to be. Again, we'll break that down more in class because I know it could be a little bit confusing. Again, a couple other components of our solar system that the nebular theory explains. Again, how planets form with planetesimals and protoplanets. So weak surface forces held dust grains together, which formed loose balls of dust. As these balls of dust collided, they grew larger and larger. So again, what didn't become the sun, again, there's other particles of dust out there. They collided, they grew larger and larger, and they formed what are called planetesimals, which were asteroid-like bodies that eventually combined to form planets. and the process of them growing is called accretion. So these, again, definitely write these two words down, which is just the process of adding mass by colliding with one another. So accretion allows you to increase in size. Again, two things collide, they basically they combine to form one bigger mass, and that is called accretion. Again, talk about this more as we get going in class, but this just give you a little bit of introduction. At about 1 kilometer in diameter, planetesimals began to exert a significant gravitational attraction on nearby objects. They attracted more material, causing them to grow even faster. So again, bigger you are, the more gravitational pull you have. So once you add one thing, then you become bigger, your gravitational pull gets bigger, and it just kind of keeps compounding. The result was the accretion of planetesimals into a much smaller number of what are moon-sized, what were called protoplanets. And proto usually just means before. Like, again, if you think of an invention, someone makes a prototype, that's what comes before. So a protoplanet is what comes before a planet. And then protoplanets join to form the current planets in a series of immense collisions. So accretion, again, they collide, they form. Again, when protoplanets start colliding, the collisions are much greater, much more explosive, and again, just because of their immense amount of size that they have going on there. And the nebular theory provides an explanation for the current motions of the sun, planets, and most moons, because nearly all revolve in the direction that the protoplanetary disk was originally spinning. So that orbit, again, that spinning motion that was present early on in the formation of the solar system, still exists in the fact that our planets are orbiting in the same direction that that disk was spinning. And so the next thing that it's going to talk about is how why we have inner rockier planets and then farther out gas giants. Again, they're going to talk about this key concept here in a moment, so I'm not going to spend too much time on it. Again, another key concept there, but like I said, they're going to explain it more in depth here. At lower pressures, such as those found in space, cooling materials generally condense directly from a gas into a solid. So when the solar system formed, temperatures near the sun were very high, so the rocky materials condensed, but water and ice-forming materials did not. So the high temperature material, so the rocks, again, were able to condense, again, forming our core, forming our mantle, forming our crust. However, things on the surface, like water and other materials, again, they were not allowed to condense. They kind of still existed as gas and possibly as liquids, which kind of led to the rockier planets being formed, again, closer to the sun because the temperature allowed that to happen. Ice-forming materials could condense in the outer solar system because it was much colder, so that's kind of why we have those gas planets there. As the outer planets grew, their gravity increased, and they were able to capture hydrogen and helium gas. Okay. Then astronomers have also been able to observe protoplanetary disks around distant newborn stars. So this process that we're describing, again, just described there, tried to describe, hopefully made some sense, around distant newborn stars. So that gives more evidence that this theory is correct. They have also detected more than 100 planets in orbit around distant stars, so this is not just happening in our solar system. There are many other solar systems out there. Evidence of planets forming around other stars, plus the result of computer simulations, provide support for the nebular theory. So again, it is a theory, it is what we accept to be true, there is evidence to support it, but again, going along with that weird theory, if something else comes up, it could possibly be altered, but in order to make it this far, there is ample amount of evidence to support where our solar system came from. The Hubble Space Telescope took this photo of what we thought to be a protoplanetary disk around several young stars. So again, that process could be in action right now, again, close that we can actually observe it, close enough, I'm sorry, that we can actually observe it with our Hubble Space Telescope, which again, it still is pretty far away, but again, giving more proof that this actually is in fact going on. Again, I know that sounded complex. We will break it down more in class, so make sure you let me know if you have any questions.